Hi, my name is Alex Bolazel. I'm a security researcher at For All Secure, and I'm here to present my research on reverse engineering Windows Defender's binary emulator. This is a follow-up to my talk at REcon Brussels, where I talked about the JavaScript engine, but there's really no overlap. You don't have to have seen that talk to appreciate this one or to understand this one. They're just two different dynamic analysis systems inside Windows Defender. A little about me. As I said, I'm a security researcher at For All Secure. That's the company that won the DARPA Cyber Grand Challenge a couple years ago. I just came on there recently, so I wasn't part of that victory, unfortunately. But do that kind of research. I also do firmware reversing and sour policy at Riverloop Security. I'm a very proud alumnus of RPI and RPI-Sec. This is my 5th REcon Montreal, but my first time presenting, so it's great to be here on stage. And before I get into the presentation, these are my personal views and opinions and whatever else, not those of any employer of mine. So an outline of this talk, I'm going to go through an introduction, then talk about tooling and process, then the actual reversing itself, and then a conclusion. So Windows Defender is Windows' built-in antivirus software. The Defender name now seems to cover kind of any security mitigation or security feature built into Windows. But here we're specifically talking about the original Windows Defender, the actual antivirus engine. Not Windows Defender ATP, Application Guard, Exploit Guard, EMET, any of those other technologies that kind of get lumped under this Windows Defender name. Just the original AV. And the focus of this talk is reversing the binary emulator, which scans potentially malicious Windows PE binaries on the endpoint. Not going to drop any ODAs or demonstrate anti-analysis techniques, but I would say if you're paying attention, you'll notice different techniques you could use to evade and break this emulator, and some of the attack surface within it that you could use for exploiting it to break out and prevesc inside the emulator. So my motivation, a lot of people saw this tweet. Tavis Normandy and some other people at Project Zero found some bugs in Defender. This first tweet was actually Tavis and Natalie found a bug in the JavaScript engine. That was the research I went and presented at REcon Brussels all about how the JavaScript engine works. But basically, this tweet and all this excitement around Windows Defender from Project Zero got me excited about looking at it, and I decided to do a very deep, multi-month reverse engineering of the engine and go a lot deeper than just maybe the bugs you might have seen dropped, here and there. I'd done a lot of work analyzing antiviruses before. I did some work in college on a project called AV Leak, where we did side channel attacks on antivirus emulators and presented that at some conferences. You can look it up. And I found overall, having done all this research and done a lot of my own reversing, that there's a lot of uninformed public discussion about antivirus internals and how they might work, but there's very little actual public work on reversing them. So I had this background, I had this interest in Defender, went ahead and did all this research. Defender has a huge AV market share, so if you want to think, why does this matter? Why is this an important software to reverse engineer? Over 50% of Windows 10 devices have Defender running this particular Windows Defender antivirus. And also, attack surface-wise, it runs unsandboxed as NT authority system. So if you can have an exploit from inside Defender, that's first your initial RCE, you're running code in this box, you have a prevesc, and you're also running inside an AV, so kind of AV bypass. It's also incredibly easy for attackers to reach. I haven't tried this myself, but I've heard from friends that it's as easy as sending an email to someone's Gmail account, and then Gmail will cache and download the attachment, and then that attachment, as it hits disk and is cached, that's enough for Defender to step in and start scanning it. So it's actually pretty good if you want to hit someone remotely. You could send them an executable that would get run in this emulator. Just a brief recap of what I presented at REcon Brussels, the JavaScript research. This bit.ly link will take you to a link to that slides if you want to see them. Again, there's no overlap with this talk and that talk, other than just a brief refresher right here. There's some common themes you will see, though, that are in the JavaScript engine and also here in the Windows engine. So there's a JavaScript engine used for analysis of potentially malicious binary code, or code that I reversed from binary. I used a custom loader and shell with help from Rolf Rolls, who helped write this. You'll see here with the binary emulator also used a similar setup, a custom shell. Throughout the JavaScript engine, I found AV instrumentation callbacks that would inform the heuristic engine in the AV about what actions the JavaScript was taking. And I also found in general that Microsoft made the choice of security at the cost of performance, to the point where they knocked out all garbage collection and just never freed anything after a couple years after frees were found. So to talk about antivirus emulators and what these are, AV emulators are used to conduct dynamic analysis of potentially malicious binaries on the endpoint. So these are really common in any commercial AV. A lot of also next-gen AV products as well also include emulators. So they will go and step in and emulate your code on the endpoint and try to make a determination about whether it's malicious or not. Emulation involves first loading a potentially unknown binary that you can't identify with simpler heuristics like hashes or other heuristics. This is a very expensive type of analysis, so you're only going to do it when you're really not sure about a particular binary you see. You'll begin running that binary and run until some termination conditions such as length of time, number of instructions executed, number of API calls, amount of memory used, and so forth. Lots of different heuristics that you use. You don't want to bog someone's computer down too much with this expensive analysis. And throughout this run, you're going to collect heuristic observations about runtime behavior and look for signatures you might drop to disk or in memory. So if, for example, your malware unpacks at runtime, I can scan in memory and see what code is it put there in memory, and maybe I have a signature for that. Or if the malware, say, calls create file and write to file in the emulator, I can look what it wrote to file and scan that if it's simply just a dropper. It's important to make clear these engines are emulating Windows and CPUs and all the facilities of a modern computer, but they're not like a full-on VM. This is not a VMware or a QEMU sort of situation. This is an emulation of CPU, an emulation of the Windows API, and all the other facilities that a modern computer might have. But it's not going to be as high fidelity or as complete as those emulations. You're not running a full Windows kernel or anything like that. Emulator components, generally, as I said, you need CPU emulation, OS API emulation, an emulated environment, such as a file system, fake settings, maybe fake network connectivity, a fake registry. And throughout that, you need to have your antivirus instrumentation on callbacks, so you can inform the AV about what the malware inside is doing. Now, as I said, there's not a lot of public research on AVs. I did some work in college. Andrew Fasano, who was my collaborator on that, is here. Called AV Leak. There's also, obviously, Tavis Ormandy's bugs. And I actually did find one talk that Halvar Flake pointed me to. In 2008, a developer at Defender gave a pretty in-depth talk about how their CPU emulator works from the perspective of an AV industry developer. It's a really neat talk and very ahead of its time. They were lifting code up into an intermediate representation and emulating it, and this was 10 years ago at least. But generally, at least as far as I could find, and I've done an extensive survey, no one has ever really gone and talked about how an AV emulator works. So I hope this presentation will be novel and interesting to people. So that concludes the introduction. Moving into talking about tooling and process, how I did what I did. So monthly, Microsoft releases this bundle mpengine.dll. It's about, say, 110 megabytes or so. A big executable that will unpack and release these different files. Our target is their mpengine.dll, the actual main scanning engine for Defender. There are other parts of Defender that do things like present a GUI or do like runtime hooking or getting process notifications or whatever. This is the core scanning engine of Defender. This is where you're going to use signatures and hashes and heuristic scans, unpackers, different parsers for different file types like PDF or whatever other file type. This is where the emulation happens. So this is really the core detection engine of the antivirus, but we're not talking about hooks into SSDTs or anything like that. It's available 32-bit, 64-bit, and you also have these other files, the VDM files, that ostensibly are signatures. They're pretty big files. I haven't gone and reversed them in depth how they work, but I've noticed that they have a lot of information that the emulator needs to run, so runtime configuration and signatures, I guess, as well in those. I did a pretty standard process of static reversing combined with dynamic analysis, but I did use some unique tools from dynamic analysis that I do want to talk about. Static analysis-wise, IDA, this is a huge binary. It's 11 megabytes, about 30,000 functions, so really, really large. What's really nice about that is, despite it being so large and difficult to navigate, Microsoft does publish PDBs, so we get symbols from Microsoft, which is nice. And I also used bindiff to do some patch diffing to understand some of the mitigations introduced after Project Zero released some vulnerabilities and seeing how those evolved over time. Now, the dynamic analysis side was a little more interesting. I had to use a custom loader in order to enable my analysis. And this is a common problem when you look at antivirus software. Getting introspection into these very large engines can be difficult. Defender, in particular, runs as a protected process, so you can't even debug it if you're running as admin on your local Windows box. You have to step in with a kernel debugger. Scanning on demand can be difficult. If, like for many AVs, you might have a GUI that you select a file you want to scan, and that's a pain when you want to scan a file programmatically. You want something like a command line interface where you can script the scanning or whatever else. And also, importantly, code reachability may be configuration or heuristic dependent. So there may be communication with the cloud to determine what kind of scans to use. There may be registry settings on your local box to determine what kind of scanning to use. They might not scan the same file with an expensive analysis multiple times over. I found this was true with Defender. If you passed it the same file twice in a row, it would not emulate that file a second time because emulation is a very expensive analysis. It would only emulate it the first time and then just store off a hash and say, hey, we've already emulated this. The solution is to use a custom loader and call directly into functions that initiate scanning. For this project, I did use a loader that Tavis Ormandy created called Load Library. I'm sure a lot of you may have seen this. And Tavis created two tools, MP Client and MP Script. MP Client is what I used. It basically exposes the main scanning interface for Defender. So you just pass it a buffer, and it'll go scan that buffer. So if you pass it a PDF, it'll scan it as a PDF. You pass it a Flash file, it'll go down the Flash file scanning routines. You pass it a PE file, it'll go scan it potentially in the emulator. So that's how I did this work. I just want to talk a little bit about how Tavis's load library system works, because a lot of people have maybe seen this project but haven't actually used it. This runs on Linux, and Tavis did a custom PE loader to load mpengine.dll into memory and do all the relocations and everything. Then you have the import address table. That's patched up with some WinAPI emulation. So a function like create file gets shimmed out to fopen, write file to fwrite, and so forth. Inside this engine, you have the emulator. We have on the outside a malware binary. And then we call this function rsignal that passes this buffer of data to be scanned into the emulator. And the emulator comes back with a determination of what the malware was. So let me just quickly demo this. This is the base MP client rather, no modifications. As I'm going to talk about later in this presentation, I built an extensive suite of modifications to MP client and customized it with several thousand lines of code to enable my sorts of analyses. But let's show you here just scanning the ecar file. We catify, you can see it's the standard ecar file. And here we scan it, and we just get a termination, threat virus, DOS, ecar test file identified. Pretty boring and not a lot of rich information about how that was determined, what went on. We just get this termination. This is what this particular binary you asked me to scan was. In addition to dynamic analysis with MP client, I instrumented MP client with some binary coverage tooling. In particular, I used a tool called Lighthouse, developed by Marcus, who's a fellow alumnus from RPISec and is doing a startup called Ret2 Systems. He used a pin tool to do this kind of tracing. And the reason I did this is I think that breakpoints can be a little too granular when you're looking at something this extensive and large. Breakpoints are great when you know I want to break here and see when this is called. But in a system like this with 30,000 functions, it's very helpful just to know what particular functions got hit during a run. I just want a trace of execution. So that's why I used a code coverage tool like this. I thought this was funny. Just 2 days ago, Halvar Flake was giving a keynote about problems in reverse engineering. It's actually a great talk. I do highly recommend it. But one of his examples of how reversing tooling is difficult to use was that it's difficult to collect coverage traces from mpengine.dll. I would have to agree with him. This was difficult to do, but I got it working. Let me just show you briefly how the timeline of my coverage trace tracing. We have our engine startup. We have all these very expensive operations like engine startup that millions or trillions of instructions get executed, loading files in from those VDM files. Those files can be like 60 to 100 megabytes each, so lots of parsing and all this kind of stuff we don't really care about. Then the initial scan, as we pass in a buffer to be scanned, we don't care about that. The emulator getting started, all the C++ objects that run the emulator getting instantiated, and so on and so forth. Then there's a brief point where our malware is being emulated inside this emulator, and we care about that. We want to see what code can our malware hit while it's being emulated. So I was able to hook some functions internal to the emulator to let me get some enlightenment about when the emulation is running and when it's not. So particular from winexec, I made a malware binary that calls winexec immediately, and then the emulator calls exit process at the end of emulation. So I can just, using these hooks, I can just trace from start to end of emulation. And then at the end, we don't care about emulator teardown. So it's nice to be able to collect this very brief snapshot of emulation right there. Just a brief demo of that, showing you how I use this tooling. You'll see here, this is the lighthouse pane on the side. And here I've, looking at, I can have a composable view. Let's see the CPU ID instruction. We can see here that CPU ID got coverage. The blue means the basic block was hit. And you'll see here that we went down this particular branch, down to the push 3, and we didn't hit these other branches. I can then also look at other things like what particular DLL functions were called. And I can see that, say, getThreadContext was called during this emulation. This is an emulation of the function getThreadContext, or the function isVDLL was called. And we went down these branches and not other ones. It's also nice because I can store multiple traces. So here's another trace that's a little more full. We hit a lot more of these DLL functions, or I could look at x86 and see here we hit 67% of the functions with the name x86 in them. Now in this other trace we hit 22% or 21%. So this is something that I found very helpful in doing this sort of reversing, getting this big picture of coverage and what I hit when I scanned certain binaries through the emulator. That concludes the tooling and process section. Does anyone have any questions before I move into the reversing and explaining how the emulator works and what I found? All right, I don't see any questions. We're going to talk about the reversing, and this is going to be in 3 parts. First, kind of a background and initialization of the emulator, then CPU emulation, and then all about the Windows emulation and instrumentation. That's really the meat of the presentation, how the Windows emulator itself works. As I said, we have this RSignal function that's kind of a main entry point to Defender scanning. And this is a very expensive analysis. This is only going to be invoked on executables that Defender really doesn't recognize and can't classify with other simpler analyses. Building binaries to get consistently emulated is itself a challenge, and that's something I have some more slides on later. But it's not as simple as just creating a P file and running it. You have to sometimes massage the linker and the compiler, remove fancy instructions, remove links to obscure libraries, and so forth. First thing the emulator needs to do is just initialize itself, allocate memory, instantiate those various C++ objects that are used throughout the emulation session, load the binary, initialize virtual DLLs, which we're going to talk about, in the process memory space. In the same way, on a real Windows system, you start a process, you have to load those image sections of those different DLLs into the process and patch up the IAT. You have to do that here as well, but we're all in an emulator, so you have virtual DLLs and patching up all this virtual memory. And throughout this process, they're collecting heuristic measurements about the binary. You can see here like suspicious section name or imports an unknown DLL. You'll see them here checking, do you import a function from API MS? You can go look at some of Alec Ionescu's talks here before about all these API MS, these min-win things. Here they'll process the redirections, API set redirect, you can see here in the pound define. You'll also see things like they set up the image name. If you pass Defender a DLL, it'll say that you're loaded in iexplore.exe. If you pass it an exe, it'll say that your name is myapp.exe. This sort of thing is obviously something you could use for evasion. You could write malware that says, if my name is myapp.exe, don't run. And in fact, if you Google this string, you probably will find some online malware reports where you can find malware that has the string in it, ostensibly because they know that Defender uses this particular name and they don't want to run if they see that. All right, getting into CPU emulation. Technically, Defender really uses dynamic translation, not emulation. And what they do is they lift all the CPU, the actual code, into an intermediate representation, and then dump it out in the sanitized x86. And they will remove complex instructions they can't emulate, they'll rewrite things, they'll change things, and it's all done a basic block at a time. This subsystem is incredibly complicated, and it's something I didn't spend a lot of time reversing. I spent more time reversing the Windows emulations themselves. But I do want to talk a little bit about this. You'll also see here they support 9 different architectures, including a full 16-bit environment, which is crazy, so full like DOS 16-bit emulation. Here I mainly looked at Windows 32-bit emulation. I didn't look at the DOS emulator, but that's a really neat whole other subsystem someone could go look at. There's also things like support for ARM. Very impressive. They support VM Protect, so they can lift VM Protect opcodes up into an intermediate representation and then dump those out in x86 to emulate them. So there's some IL lifting, incredibly intimidating control flow graph here, difficult to look at. Didn't spend a whole lot of time reversing that, but you'll see all these functions, ARM to IL, net to IL, VMP to IL, x86 to IL. These are all translators of a particular CPU architecture's code up into this Defender-specific intermediate representation. Then this IL can be run in software with another incredibly intimidating control flow graph. I didn't actually observe this being run during my research, but I was able to reverse some of it out, and you can see unique things here. Like, for example, we see these pound defines for XOR 8, XOR 16, and XOR 32, and you can see that those line up with the particular switch statements and the cases. And if you look at the actual code there, you can see very clearly that these are emulating, say, an 8-bit XOR, XOR DL. Then we move to the 16-bit with case 108, XOR DX, and then 32-bit case XOR EDX. So you can see that this is a software emulation of an actual XOR instruction. What I did observe being emulated, or being used during emulation, was this, the x86 JIT compiler. So in this case, the IL code is translated down into 32-bit x86 code and executed a basic block at a time. Kind of similar to QEMU, where QEMU is going to lift your code up and then dump it out, basic block at a time, these translation blocks. And in some cases, you can just run the raw code. So for example, we see here the function for IL to x86, and this is for a load LEA, register 32, immediate 32. And you'll see here that they put out this 858D. The LEA opcode itself, without any arguments, is 8D. So you can see that in the red boxes. And then they have to XOR this with a mask for the particular register being used in this operation. And this is then put into an executable region and then executed. Now, for instructions that are too complex, they will actually generate a call directly into a what's called an escape function that provides native emulation of a complex instruction. For example, CPU ID. And I've highlighted here in red boxes the sort of actions that happen there. If you have an escape function that needs to happen, such as a CPU ID, they'll emit a particular escape identifier in the IL, and then they'll grab the particular function pointer to that function that emulates, say, CPU ID, and then they'll actually generate on the fly here this code that, move ECX EVP, move EAX an immediate, and then call EAX. And what you can see here is, the E9, 98, 9H, so forth. Those are, when disassembled, that's actually a move ECX EVP. And then here, 8B, or B8 rather, is move EAX immediate. Then we're sticking the immediate into the jittered out bytecode, or x86 code, and then calling it. So the CPU ID instruction actually translates to a call into Windows Defender's emulator to provide emulation for that complex function. Here's these architecture-specific escape handlers. They're for architecture-specific events. You'll see ARM has a lot of instructions that cannot be easily modeled in their IL or x86, so like qadd, qsub, sm, lol. These instructions get emulated natively. Here in x86, we have things like the load selector or CPU ID, and these get emulated here. Just show you the CPU ID handler as an example. I wrote a malware binary that did move EAX 80001. Ran this. I collected coverage with Lighthouse, as I showed you earlier. And what I saw was this basic block coverage. And you can see here that the block for this same immediate 80001 we see that we match that, and we continue down this block because we hit that particular instruction. We don't go into the path of comparing it's 8002, 8003, and so forth. This sort of example, I think, shows why coverage-based tracing can be particularly helpful for a complex system like this, where I'm actually compiling these malware binaries and sticking them in the emulator, and I want to see what code can I hit when I'm inside. That concludes the CPU emulation portion. Now moving into talking about Windows emulation instrumentation. And this is really the meat of the presentation, the longest section. And it's going to be actually in 6 parts. First, we're going to talk about instrumenting the emulator itself, then move through the user mode environment, the user mode code, the user kernel transitions and interaction, the kernel internals, and then we're going to conclude by talking about AV instrumentation that's woven throughout this whole process that the Windows Defender wants to collect heuristic information and observations about the malware under analysis. First, we need to talk about instrumenting the emulator. So there's a big problem, which is that the only visibility we have in engine behavior is malware detection, basically. Obviously, we can't step in with breakpoints and do coverage-based tracing, but if we want to just pull information out of the emulator and observe what's going on inside, all we get is malware detection. This, of course, can be exploited as sort of a side channel to extract information. That's the work I did a couple of years ago in college called AV Leak. We showed how you could use malware detection to extract information from AV emulators. It's quite simple. You do things like, if this particular API returned 1, drop malware, otherwise don't. And you can see how you could build this out to a larger and richer side channel to rapidly extract information. But it's slow and it's difficult. And we want to get more information than just malware detection out. So the solution I came up with, and this was with the help of my friend Mark, who suggested the idea, give our malware kind of a malware's eyes view. Let's see the emulator from inside. And we do that by hooking certain Windows APIs that get invoked at runtime as the malware calls particular Windows APIs. So there are functions that provide emulation of the Windows API, and we'll have our malware call them with controlled arguments in order to share data with the outside. We can also create a two-way I/O channel, and that's something I did as well. So you can do things like a fuzzer, where you generate inputs to be fuzzed on the outside and then pass them into the emulator and throw them against emulated APIs. So again, this is Tavis's MP client binary that I talked about before. In its unmodified state, it looks kind of like this. And I've added here the gsyscalls table. This is a table of 119 functions that are emulated in native code. So actually native C code, compiled emulations. And we escape out of the emulator and step into those when certain APIs are called. There are also thousands of APIs that are run in emulator, which I'm going to talk about in a minute. But these are particularly complex functions that get emulated in native code. And they're actually in mpengine.dll. So we can hook these functions. So I'm going to show here, I hooked output debug string A. And I actually made, whenever the malware on the inside of the emulator calls output debug string, we're going to print to standard out. I also hooked winexec for some other actions. I'm not going to address as many of those here today. Mainly, we're going to show what we can do with output debug string. And this innovation is that we can now scan malware, and we can take observations about what's inside the emulator and share them with outside, as simple as literally just printing a string. I need to talk a little bit about how I did that before I do a demo. So there's this function that I've shown here at the top with hexarrays output that's called whenever the malware inside the emulator calls kernel32 output debug string A. I here pulled out the RVA of the function, and I can set some hooks and hook that function pointer inside the emulator and replace it with my own function. And then I implemented my own version of this kernel32 DLL output debug string A function. And let's walk through how that works. So right here we have our implementation showing the Sublime text in the center, and the IDA version is at top. First thing we do, we have to have the same function prototype. You do the right declaration, that's cdecl. We don't know how this PE-vars T structure works. It's a very large structure. So I just declare this as a void pointer that we get. The first thing we need to do is peel off parameters that are passed to our function. So we use a function here called parameters1. And what this does is it takes this PE-vars T blob, this massive structure that's passed to us, and it will actually go in and grab the virtual stack pointer and map it memory and pull off whatever is there at the virtual stack pointer and retrieve that many arguments. It's more complex than just that, but basically it takes this big structure and it tells us what arguments were passed into our function. And these parameters are just addresses with the emulator's virtual memory. These are not real pointers that we can actually use and dereference. These are basically uint32s that say, at this address in the emulator was this argument. This is sort of akin to if you've ever worked with Unicorn Engine, where you're going to have to map that memory in, with, say, like UC map dword or whatever it is in Unicorn. Windows Defender provides a similar API to mapping in memory. Of course, this isn't a publicly exposed API. This is all internal to Defender. And I have to call directly into these functions. I have to save offsets for them and call them directly in order to use them. After we get that parameter address, I call a getString function. This uses a Defender internal function to retrieve and map a virtual address into a real address where I have a real pointer. And then I can just print that standard out. So let's see this in action. So here, we're booting up, running, and here we see output debug string, hello recon. Let me show you the source for this. This is here in this sort of malware binary that I've created. I called hello recon. And when I scan this binary, we go into the emulator, we get scanned, we call output debug string A, and then because I have this hook gets invoked, I can print that to standard out. Now, this is a live demo. Let's try adding another message. Anyone have any suggestions what I should have the malware inside say? Any ideas? All right. Welcome to Montreal. All right. Let's build this. Go back here. Again, we're going to scan this file again. And now you'll see hello recon and then welcome to Montreal come out on the terminal. And there it is right there at the bottom, welcome to Montreal. So obviously here we're just printing out our own strings, but this is a very powerful tool we can use to explore the emulator from inside. And we can take any observation about time, what we see, virtual processes, different things that are loaded at runtime that I can't see statically in IDA. I can see all of those from inside. I can see the virtualized environment. I also thought I'd show you just a bit about some of these hooks. So here you'll see I have a big table of offsets, and this is where these parameters functions are. This is where mmapex is, the functions you want to hook are. I then have my hook setting function that'll set these hooks. I have various functions that'll call into Defender itself. So for example, getString actually calls into PE read string EX. That's the Defender native function to do this. That function is a very strange calling convention where it's a fast call, but it's optimized. It's optimized kind of weirdly because there's a uint64 in one of the first two arguments, and fast call doesn't work. Fast call works with native register size arguments. So I could have massaged GCC enough to get it work, but I thought it was easier just to write assembly shims for this. So I shimmed these out to assembly. These are standard calling convention, and then these rearrange the registers in the stack in order to call into these functions inside Windows Defender at runtime. One more thing I thought I'd show you. Here we're just doing this kind of simple output, just saying, hey, we're booting up, and we're going to show this output debug string. I can run this in verbose mode, and I can show you everything that's going on. So you see all these hooks that I'm setting. These are the RVAs and the actual resolved addresses inside Defender. Here you see these various hooks getting invoked, various things getting called as we start up. We said, hey, we're gonna call this function. Then we do output debug string A, and we get these virtual addresses 0x403A. You can see that's clearly a pointer to the .data section of the malware inside. And then finally that resolves into printing hello recon, and I log entry and exit of this function. This is very helpful for debugging, having this rich information, but obviously you don't need this every time. You just want to print a simple string to the stream. In terms of the binary that I built, I showed that briefly, kind of this malware binary. Standard Windows binary built with Visual Studio 2017. And this binary communicates with the outside world using output debug string A and other hooked functions. As I said, it can be difficult to get consistently emulated. You'll have to massage your linker settings. You don't maybe target the most modern Windows build. You don't want to call unsupported functions, use particularly fancy instructions that might cause emulation to stop. It's all sort of heuristic. I find it's just easy to strip down, remove things you link, remove optimizations, target an old version of Windows. I'm sure someone at Microsoft could tell me I'm all wrong, and I could have got it emulated this way or that. But I found a way to get malware code consistently emulated, and I ran with that and used it. All right, that concludes talking about the instrumentation that I used. Now let's talk about what I found using that instrumentation. So the first thing I want to talk about is the simplest, the user mode environment. This is the emulator environment presented to the malware, trying to get the malware to run inside. So we have an entire virtual file system, about 1,500 functions. I dumped this whole file system, and so this is all virtualized. This is to make the malware think it's really running. And you want to have functions that are kind of juicy targets for the malware. You want it to open files and send them over the cloud or whatever. You want to present an environment where the malware is going to run and do malicious stuff, like infecting other files, like reading sensitive configurations, like things like that. So let's just go ahead and show dumping the file system. So here we are actually running through the entire file system and dumping each file that the malware sees. It's iterating over every file in the file system and spitting it out. This really takes only about 2 seconds, but as I was preparing this demo, I found that as I created a binary, Defender started not wanting to emulate it for some reason as I iterated over the files. I solved that by just adding an output debug string during that iteration, and I don't know why that worked. I'm thinking maybe there's some sort of heuristic that the emulator just sees it enumerating files, it thinks it'll be an expensive loop, it doesn't want to run it. So anyhow, we have a slowdown just because of that, because of this process of f-flushing standard out every time we dump a file. It actually runs a lot faster. Anyhow, we've dumped the entire virtual file system. This is what our malware on the inside sees. And this is important because these files in the file system are not available statically in mpengine.dll. They appear to be loaded from these VDM files at runtime, best I can tell. And we can go over and look at this virtual file system here. So here it is, dumped. And some of these files are empty. Some of them are actual executables or DLLs. Some of them are text files like this that says goat over and over again. All sorts of stuff, various DLLs you can see. These are all just emulated binaries kind of inside of this fake file system. So I showed you the goat file. If you Google goat file, you'll find that this is kind of an AV industry internal term, particularly kind of an old school term for a file used in testing a computer virus. You want to see, does the virus infect this file, or does it read it or whatever? You'll actually see this in other AVs. I've done other work where I've found files that say goat or called goat.txt or whatever it may be. So this is kind of a goat file. And it's called AAA touchmenot.txt. Kind of funny. You'll also find fake config files that you can clearly see that these are written by a human who wrote something like blah blah and just generic fake SQL code, just fake stuff to convince the malware it's running in a real environment. You have a virtual registry with thousands of entries, references to things like World of Warcraft and Tencent and different programs that real users use, like CCleaner. There's also a virtual process listing. We can dump that, and we can look at other fake processes running inside the emulator. Again, these are not real processes. This is fake processes that the malware often enumerates processes to see if AVs are running or target processes it wants to infect are running, and we can run through that and dump them by PID and see things like WinLogin, SMSS, Firefox, Notepad, Google Talk, various AVs, antivirus.exe, AVP, Norton, and so forth, KAV, Kaspersky. This is, again, kind of making this environment the malware is likely to run and do something malicious. You'll see here this listing, and there at the bottom in yellow is myapp.exe, our actual application running under this name, myapp. Moving to talking about user mode code, beyond just the environment we see there, we can talk about the code we see. As I showed, there's lots of DLLs inside of there. And there are really two types of Windows API functions in the real Windows and also in the emulator. Those that stay in user mode, and in that case, they're going to stay inside the emulator, and those that resolve into a syscall where they trap to native emulation. And just like real Windows DLLs, we have what's called VDLLs, virtual DLLs, that are actual DLL PE files and get dynamically loaded into the engine. And we can reverse them, because after I dump them, they are just PE files. We can pop them in IDA and reverse them. And you'll find funny things like this, a hard-coded username, John Doe. So when I call it get username A inside the emulator, this particular emulation routine kicks in and returns John Doe. The computer name is HAL 9000, as in Space Odyssey, the movie. So again, these are sort of things you could write malware that looks for this username or this computer name and then doesn't run. But they're very obvious, very simple. You'll also see things like knocked-out functions that just return 0. Lots of functions that are too complex to emulate that just return 0 or 1 or just trap or whatever it may be. So if you run RPC enable WIMI trace, you're just going to get an exit process. It's just going to die. So simple functions that are common are emulated, and complex ones are not. You'll find unique strings like this. WS232 has German IP addresses, references to German websites like Gutfrog or Avira, and then strings indicating things like MP, as in mpengine. Again, you could use this to write evasive malware that looks for these traits. You'll find things like WinINet, which provides internet emulation, or internet implementation on a real Windows system. Here they've implemented internet connectivity with kind of a loopback on the local file system. So if you open URL, they give you a handle to this file internal remote exe, and when you read from file, you just pass in a handle, and they end up just reading from this file on a local loopback. So there's actually no internet emulation that I could find in Defender. It's all implemented in this kind of local loopback where you just get a handle, which is this opaque structure, then you can then read from or write from or whatever it may be. You'll find in these VDLs interesting debug strings, clearly evidence that people at Microsoft actually built these, and you'll see mpengine, a core, MAV utils, and so forth. So these were clearly built in some build process and then stuck into Defender and packaged up for the simulation process. All right. Now moving into talking about user-kernel interaction and the transitions from user mode into kernel mode. In Defender, kernel mode is implemented in native functions, natively implemented C code. So there's a particular unique instruction called API call that's used to transition from inside the emulator to the outside world. This is very much akin to the syscall instruction on a real system, or to a hypercall in a hypervisor, or if you've looked at things like AFL Triforce, they have a special AFL instruction that informs AFL what's happening inside QEMU, very much like that. When this unique API call instruction is called, we're going to trap out of the emulator context and the dynamic translation context of this virtual CPU, and we're going to trap into native code that implements a native emulation. This is sort of what we saw with the output debug string A function. When output debug string A is called, we actually trap into our native code to implement that function. And this custom opcode, this is not a real opcode. IDA does not support this IDA processor extension module to do it. This is something Tavis Ormandy abused in one of his exploits. It's since been ostensibly patched, but we'll talk about some mitigation. There are ways around that maybe later this summer. The opcode is structured like this: 0f, ff, f0, and then a 4-byte immediate. The immediate is formed by XORing of the CRC32 of the DLL name and the function name, which looks like this. Kernel 32 DLL, XOR with the CRC of output debug string A. We get this immediate, and we put them all together. And this particular instruction is API call kernel 32 output debug string A. So when this instruction is run on the virtual CPU, it generates a call into that emulation for output debug string A, our native emulation that we showed in our hooked function as well. This is dispatched through this escape table that I talked about earlier in the virtual CPU. And there's various function pointers to these functions. These are the actual function pointers that I was hooking when I showed you how I hooked output debug string A. They're stuck in this table, which is basically the CRC is the immediate value that goes in that API call opcode, and then the pointer is a pointer to the function implementing that particular emulation. Use some IDA-Python to extract all of those, and I'll show them now. Here's native DLL functions. The yellow ones are ones that are unique to Defender that aren't real Windows functions. These are used in the AV instrumentation process for Defender. Here's more functions from NTDLL. You'll see weird functions like a VFS. These are unique low-level access functions to the virtual file system. This is some attack surface that Tavis Ormandy used in one of his exploits, was the VFS system, which has, as I said, ostensibly since been blocked off from access by users inside the emulator. So output debug string A, this was that function we showed earlier. Here inside the VDLL, we see the emulation for it where it does some things like set a count how many times this function was called, change the SEH limit. Then it calls API call kernel 32 output debug string A, which looks like this. You'll see here the API call instruction that's going to trap into the native emulation when it's executed. This is, again, all in the virtual CPU. This is inside emulator, inside Defender, running across that dynamic translation engine. And at that point, we trap out with API call, and we hit this native emulation function. Again, this is the function we hooked. This API call instruction is what generates that trap out, akin to doing a syscall on a real Windows system. As I said, API call is not a real instruction. So when I reversed these DLLs, IDA was choking on it, and we get this ugly output here. The solution is to implement a processor extension module to support API called disassembly. And you get this nice disassembly here where we say API call, and even when you do hex arrays, you get an intrinsic there where it shows this assembly block. So just a brief demo of that. We can see that this works. I'm here in the NTDLL emulation VDLL, and I can click here and I can see these various API calls. And there's all sorts of API calls strewn throughout this process. Some of them aren't even used, they're not recognized as full-on functions. Some of them are. So, as I said, this is a real DLL, 1,300 functions. Some of them do stuff, some of them don't, some of them are just knocked out. But you will see, actual emulations of various NTDLL functions and so forth. All right. Finally, talking about these native emulation functions, how they're implemented. I did show this briefly at the beginning with the output debug string a hook. But basically, all these functions have a common function signature. They take a PEVARS-T pointer. This is this big opaque structure about 0.5 MB large containing the entire emulation session in one big context. These templated parameters functions allow interaction with the parameters passed to the function, pulling them off the virtual stack. And then various return values, register state, CPU tech count can all be managed with various APIs that manipulate this one big monolithic PEVARS-T structure. You'll see here they, at the bottom, bump the vticks, the ticks in the virtual CPU. They'll set a return value and so forth. Memory can be interacted with an interface similar to that found in Unicorn Engine. We can memory map in different buffers of memory. And there are wrapper functions to make this easier, like read just a D word, read a Q word, read a string, and so forth. Read a wide string, whatever you want to do. They will map in intelligently, smartly map in virtual memory and translate that to a real pointer you can dereference and view the memory there inside the emulator. Timing. This is an important part of any emulator or VM, and it's something that's very difficult to get right. But you'll see here, they, throughout emulation, will bump the timer. In CPU ID, that incurs a 24 CPU ticks on the CPU cycle. Sleep, you'll actually have to bump the CPU count or the ticks by the length you slept for. A VFS read will incur a bump of 512 ticks on the virtual CPU. All right, now we've talked all about the user mode inside the emulator and how we transition down to the kernel mode. Now, what's the kernel mode actually look like itself, and how is the Windows NT kernel implemented inside Defender? Windows kernel facilities get emulated with this native code. So this is actual native C code written inside mpengine.dll and compiled there. Great attack surface, you can find any vulnerabilities in these native functions because these are native code running on your real system. And these traps into this code are generated when your malware calls certain functions. So we have an object manager, a whole bunch of functions for interacting with that. This is an essential part of the Windows executive. And this is how you manage handles, things like files, threads, events, mutants, semaphores. And this manages this persistent state between native API calls, akin to the way a real Windows system would have a handle table for your process and would store those handles as you run and interact with them. There are 5 types of objects inside Defender's object manager: file, thread, event, mutant, semaphore. They all inherit from this base class object manager object, and you can see here inheritance of 2 of these classes, file object and mutant object. And here you have specific fields to the file object, like mfile handle, or to the mutant object, owner thread ID, is it abandoned, and so forth. These objects can be retrieved with functions that basically pull them out of a hash map. Because they're all in C++, they're all stored as kind of an object manager object pointer, and RTTI is used to cast them to a particular unique subtype that they are. And you can see that here. Cast it if the type is 1, which is this first one. They'll check the type. In the virtual, the vtable, there's a function that says, what is my type? It'll say, I'm type 1, therefore my file object, or event object is type 3, and then they'll do RTTI to cast it to that type. I did audit all the places that these event objects are used, or these object manager objects are used. They're all accessed kind of safely, and they always check through the vtable. So I didn't find any chances for, say, type confusion. But, it's good attack surface, worth auditing. I mean, I guess there's also not really pointers there, but, it's worth checking out. Object manager is integrated throughout these virtual emulation functions. So NT object open mutant worker will open an object that you pass in a handle to, or when you try to get file information, you'll open a file object. Again, this is all through the object manager. And you can see things like if we can't retrieve the file object, we set a status to status invalid handle. We'll set that in turn to the return value of that function, setting the virtual register EAX and then returning. Our own process is emulated as 1, 2, 3, 4. Again, a unique kind of thing you could use to detect the emulator. It's kind of funny, they just hard-coded this value. So our handle is always 1, 2, 3, 4. And you'll see things like when you try to interact with the virtual processes here, you'll see that they always check, is our process 1, 2, 3, 4? If it is, then we can do things like read process memory. We can only read our own memory. Because these other processes in this emulation session are not real Windows processes, we can't actually interact with them, read or write memory to them, it just fails. So that's another unique thing. Going back here, the virtual file system, this provides native emulation for the file system. Again, this is what Tavis Ormandy attacked in one of his exploits. There's basically a virtual file system. It decomposes to being backed by kind of expandable array buffers sort of on the heap. And this is a persistent virtual file system. So you can write to a file, close the handle, reopen that file, come back to it. It'll still be there during your emulation session. There are obviously NT-DLL functions like NT-write file, NT-create file, and so forth. And these are going to call down into these deeper layer of functions, the VFS functions that do normalization and checking, or after normalization and checking. This is akin to the same way in the Windows kernel. And as you trap into the kernel, you call NT-create file. There'll be some initial sanitization, and then you'll get passed on to the rest of the kernel to do interaction with the file system. These are virtual file system specific native functions. These are ones that are below the NT level, VFS copy file, write file, and so forth. And you can see here that these VFS functions and pointers to VFS state is stored in the PE_vars_t big object that we have there. The virtual registry is not exposed for direct interaction with emulator in the same way the VFS subsystem is. But we do have the virtual registry. As I showed, we have things like World of Warcraft entries, various software that people use. Again, probably to convince malware. Maybe there's malware that looks for World of Warcraft information. They're going to enumerate the keys, and that's a strong indicator of malicious intent if they see that. Process interaction talked about. Now to close out, talking about AV instrumentation woven throughout the emulator. We have these Defender internal functions that I've summarized here. These are unique functions that do things like queue up a file for scanning. So if I write a file to disk in the virtual emulator, they'll want to queue that VFS object up to be scanned eventually, because maybe the malware I've written is just a dropper for another file. So they'll queue that up. We can alias memory. We can report malware behavior to inform detection heuristics, get metadata about those detection heuristics from inside the emulator. These are all not intended to be exposed to the malware. These are intended to be exposed to Defender internal APIs, such as those in the VDLLs, or to maybe for Defender developers to debug the interface. So you'll see this woven throughout the VDLLs, the MP report event calls. So if I call get system directory, this is evidently 12331 is the identifier for this particular function being called. If I call get current process ID, I'll get this identifier hex 33D, and I'll have the string self because we are our own process. If I enumerate some of these program paths, we'll actually call this other one 12312 with a particular path that we were enumerating and or creating a process. So you can see there's just a huge number of identifiers for actions that inside the emulator the malware takes. At the native level, these MP report event calls are implemented in the same way as the other native emulations. There's an API call instruction that traps it to native emulation, and then a particular heuristic is recorded about the emulation session that's going on. Some of these, again, can show malicious intent. Some of them trap out. So some functions will first notify and then trap out to do some native emulation, like get file size. We'll report an event, and then we'll actually call NT-DLL, get file information, whatever it may be. And some functions just report the event and continue on executing. So for example, as I showed here, get system directory just reports an event and then returns a hard-coded string. So the only time we escape from the dynamic translation, the virtualized emulator environment, is during that call to MP report event. One example of how these report events are used is here with AV processes. So you'll notice here that all AV processes in the process listing have a PID in the 700 range. So we have Kaspersky and AVP, FSAV, Norden, mpengine itself is ostensibly running Outpost, whatever. And in the terminate process emulation, they will check the PID, and if the PID is in the 700 range, they'll report a specific event for a terminate process, and then they'll append the string AV to notify. This is, it's bad enough that a piece of a binary terminates a process. But when you terminate an AV process, that's probably a very strong indicator of malicious intent, that your normal code, non-malicious code, does not kill AV processes. So they want to get this information and be informed about what's happening. NT control channel is this kind of unique backdoor interface that provides an ioctl-like interface for administering the engine. This is some of the attack surface that Tavis Ormandy hit. He, in particular, hit the load microcode opcode, or ioctl. You could pass in a buffer that would contain new microcode to reprogram the virtual CPU. And there was not really a bounds check on how many opcodes you threw in, and you could have this loop and heap corruption really bad. You end up being able to break out of the emulator if you were to exploit that vulnerability. And I've gone here and enumerated all these various different ioctls, what they do. So you can set various attributes that your malware is doing. You could say, I called this function. You can report different events. You can also query events. You can say, does Defender think that I have a unique number of imports? Does Defender think that I did this? Does Defender think that I did that? Whatever you want to do. You can initiate new scanning. You can load new microcode. You can set a breakpoint inside the emulator. There's a whole breakpoint kind of interface in Defender. This is really kind of this backdoor debug interface for the Defender developers. That concludes all the reverse engineering discussion, and now moving into the conclusion. So in summary, we covered tooling instrumentation, the CPU dynamic translation basics for x86, and then a whole lot about the Windows emulation and the environment for the Windows API for 32-bit x86 binaries. But there's a whole lot we didn't cover inside Defender, like translation for non-x86 architectures, the entire 16-bit emulation, which is a really fascinating subsystem, or .NET analysis. And these are all very rich topics. You obviously can have similar patterns to what you see here, but these are whole massive subsystems, and it's hard enough to fit all this information just in 1 hour. Now, mpengine.dll is an absolutely massive binary, and it's got all kinds of other interesting stuff to go reverse engineer, or fuzz, or whatever you might want to do with it. There's unpackers for all kinds of various packers, ACE protect, VM protect here you see. There's parsers for all kinds of formats like CX509 or LNK, PDF as well. There's an entire JavaScript engine, which I spent an hour at REcon Brussels explaining how that works in a similar way to this talk. Recommend checking out my REcon Brussels talk if you're interested in that. Other scanning engines for PDFs, 7-zip. There's a RAR VM, Halvar Flake found some vulnerabilities in that about a month or two ago. Really interesting stuff. There's a .NET engine as well. Now, in terms of my code and my information, I'll be releasing code for some of this instrumentation after Black Hat and DEF CON. Here, I only showed a little bit with the output debug string A trick, where I was passing some information out to standard out. But I, in total, wrote about 2,000 to 3,000 lines of code on top of Tavis's load library tool to instrument it. And I also wrote a couple thousand lines of code for my kind of malware binary that goes inside the emulator. I also did an article for Packer GTFO, thanks Travis, that has some more information. One, a deeper explanation of the output debug string A hook, then some patch diff and API call hacking, which I haven't touched on here. I'm going to talk some more about that later this summer at Black Hat and DEF CON, about some of the attempted mitigations Microsoft put in after Tavis started abusing the API call instruction, and how those mitigations fall short. And then also I'll share my API call disassembly module for IDA, so you can load via DLLs and disassemble them cleanly in IDA on your own system. I want to conclude by saying that people love to talk about antiviruses, what they can and can't do, and there's all kind of speculation. But there's very little ground truth about AVs. There's not a lot of talks about actually reversing them. There's plenty of talks about evading them. For example, pen testers trying to wrap a Metasploit module in a way that AV doesn't detect it or pack stuff. There's some talks about reversing certain heuristics that AV uses, but very few talks actually going in and reversing AV binaries themselves and explaining how does this AV do what it does. Here I've honed in on the emulator. That's a particular substantive of interest of mine. And again, that's pretty unique. As far as I know, no one else has talked about AV emulators for any AV product. But I hope we'll see more AV reversing talks in the future. If you search antivirus internal emulators, all the information you get is basically me, Tavis Armandi, and then Hoxian, who wrote a fantastic book called The Antivirus Hacker's Handbook. If this talk was interesting to you, I do highly recommend getting the book. It's a really great resource. I had to learn a lot of this stuff without the help of this book when I was doing this back in college, but reading the book answered a lot of my questions. So just a great book, and Hoxian's a friend. Do check out his book if you like this. So Defender was really great. I enjoyed reversing it. Custom tools are going to be necessary to do antivirus reversing. Sandboxing Defender will help security. It's currently not sandboxed. That's been in the works for, I think, over a year now since Tavis dropped his bugs. And I think people should check out other AVs. Here's some links to my Defender slides from REcon Brussels, as well as a video from another conference where I gave the talk about the JavaScript stuff. This is all on Twitter. You can go find that if you're interested in kind of the part one to this talk. Very similar layout, and just a deep dive into the JavaScript engine. And I want to thank all my friends for their help. Thanks to the REcon team for bringing me both to Brussels and here to Montreal, and to everyone else. And that's the end. Thanks. So, any questions? I've spent a lot of time reversing AVs. I'm kind of sick of reversing AVs. I mean, it's fun, but I've done a lot of it through college and now here. This whole process of the JavaScript engine and this engine as well was probably close to a year of just personal time. This was my side project. I wasn't being paid to do this. I enjoy this. This is fun. I will be presenting, as I said, later this summer at both Black Hat and DEF CON, talking more about some of the API call hacking and some other stuff. This slide deck in total, I've only shown about half my total slides, and I had about 80 slides here today. I have about 160, and you can see all kinds of backup slides that I have later here in this presentation that I haven't addressed. So go present, publish an article on Packer GTFO, and I think I'm pretty done with reversing AVs. Any other questions? Oh, yeah. I didn't. I mean, they're rewriting the code and jitting it out. I'm not sure if you would preserve the sort of semantics you need and those tight loops you need to have the speculative execution stuff work. You could try it. I also would be suspect whether you get enough CPU cycles to make those actually effective. And then, okay, worst case, you actually leak information. What do you do with it? You're inside this emulator. You'd have to break out in order to make that information useful. And at which point, if you broke out, you're already running on the native system. You can just read information. I suppose you could try it, but there's certainly much easier targets than this whole proprietary engine. You could go do this in Unicorn and actually write the code yourself and see what happens. This is very complex. And as I said, if you write code that's too complex, like if you use the RDTS-CP instruction, they'll abort execution. I'm not sure the very complex patterns you would need for, maybe speculative execution might work, but I wouldn't count on it getting consistently emulated and working and everything, but you could try it.
One of your slides seemed to indicate that this supports POSIX and OS2. Did you feed it any such binaries?
I did not. I focused on 32-bit x86 binaries, but I wouldn't be surprised. I mean, they should have at least some Windows POSIX implementation. I'm not sure about the OS2 stuff. As I said, just took me an hour, very long, lot of reversing just to find out about 32-bit Windows. I think the 16-bit like DOS environment would be something really interesting to dive into as well. Yes?
Did you find binaries that could be handled neither by the cheaper analysis methods or the emulation in Defender?
Binaries that could what?
Because you said if a binary can't be detected or whatever by the cheaper analysis methods, then it would get emulated. But there are some things that can't get emulated either. Is there stuff that can get around all of it?
I wouldn't count on that. I'm not an expert on this sort of AV functionality. My focus was on the emulation and the runtime analysis. But I presume if you gave a particularly malformed binary, There'll be lots of heuristics about the binaries, imports, the size, and so forth, that would themselves be indicators that maybe it's malicious or you don't want it running in your system. But again, I'm not entirely sure. I focused on making binaries that did get cleanly emulated and would get emulated. This is just one line of defense in this very in-depth process of protecting your computer. This is again just one particular scanning subsystem, and it informs other subsystems, and it runs if those other subsystems, as best I can tell, can't produce a clear determination about whether the binary is malicious or not.
Okay, thank you.
Thanks. Any other questions? Oh, cool.
Are you able to dump the IL that the Windows Defender uses?
I haven't tried that. It does appear to be a proprietary IL from at least looking at some like the pound defines or like the constants and defines that handle it. But I haven't actually worked on dumping it. As you saw, those are massive, huge control flow graphs, really ugly to look at manually. But insofar as they're just a massive switch case, I presume you could get pretty far with some Python scripting, just pulling out labels on, this switch goes to here, which calls a function called emulate XOR. And you could probably get a pretty good idea on what's going on there, but I haven't tried. And as far as I can tell, it's a proprietary IL. It's not anyone else's IL. I did touch on briefly, there's that presentation from hack.lu in 2008 from Bitdefender. Kind of obscure presentation, doesn't easily show up on Google. Halvar Flake pointed it my way. He said it was like a friend of his gave that presentation. That presentation talks from the AV industry developer's perspective about how the IL works for Bitdefender, and it's really very impressive that 10 years ago they were doing all these things we see now with program analysis, lifting up to an IL and dumping stuff out, and then various optimizations they can do. They seem really ahead of their time, and they were working in a unique space of malware emulation and in a space where you maybe gain from some obscurity and not talking about how your stuff works. Whereas here we have this big wave of all these talks about program analysis and vulnerability research based on lifting an IL and doing analysis. Bitdefender's case was lifting an IL and running malware. So I do recommend checking out that slide deck. It's I can pull it up here if you want to get the name. It's not the easiest thing to find really on Google. It's here, Mihai G. Sharak, Antivirus 2.0 Compilers in Disguise from hack.lu 2008. So recommend checking that out if ILs are your thing. Any other questions? All right, don't see any. I'll be in the hallway after if you have any questions you want to ask me one-on-one. Thanks so much.